So as we are starting a new experiment, we make a new dark. So that we always have a dark corresponding to our latest experiment. Okay, so then edit. No, it's right. Apply. Okay, so basically, yeah, nothing changed. It looks a bit better from the numbers. Okay, so then we now have a cadmium source here. So then we switch this on. Yeah, sure, fine. Okay. Okay. And now you can see the sprinkling, and you see also that we have a shield there because there's a small lead encapsulation with a lead tape, which is shielding this area. And then, so we make again XY selection, our histogram as before. Looks like this. And the region is okay. And so here is now the cadmium peak. This is a split pixels, the charge sharing between pixels, which because we just make a raw histogram among all the pixels, they are obviously not recombined. But most, I think 70% of Philip, of the photons are depositing most of that charge in one pixel, and that basically builds up this peak here. So now we can do again an average. 120. And which tail? This one? So this is when two photons are hitting a pixel. Let me zoom out of this a bit. So that is now the logarithmic spectrum. So this is basically one photon, and this is a 2-photon peak, and then here vaguely one can see a 3-photon peak. Obviously for 3 photons, the probability that 3 photons are hitting a pixel in the center is very low. So for 3 photons, your probability that even if one hit its center but the other ones didn't, so you get a much more smeared out peak. Nevertheless, this basically is the Poisson distribution of a very low illumination condition. No pocket synchrotrons yet. So this is 1 photon, 2 photons, 3 photon. And then there's something here.
Yes, so basically they got about the couple characteristic line.
Yes. So we can take that's much easier in this scale. So we take the cursor. We make grab and something here. That's 111, the peak position. Good enough. It's not a spectroscopic detector. Enter. So is X divided by 111 multiplied with 22 keV. Apply. Okay. So now we have the scale in keV energy. Let's go to 150 keV, and we can again go into log scale. And now is reasonably nice, so I can make a grab at this position, and that's around, well, it says 89, but that should be 88 keV. So now we have normalized the spectrum to the energy in keVs. Okay. So we see it really is a spectroscopic detector. One cannot find only the fundamental, but one can also find the second product of this decay. So then we can again make imaging, for instance, with the hit finder. So now I can say that I want to sum analog values instead of counting hits. This one really gives me all the analog ones. Then it looks first like this. And when I make a spectrum here, sort of the same. Let's take it should work. Let's see if it works. Here. Okay, so now this is a spectrum which I derived from this window, and we see why LCLS has so many monitors. That's very, very useful with this data acquisition system. So I made a hit map which shows me everything above 50 ADUs, but this time analog, not just digital. I'm not just counting yes or no. I'm keeping the value, and that basically, and then I make a histogram out of this data. And here you see that I made this hard cut at 50, but then up from that, I get, again, all the analog values. The information is completely retained. That's very advantageous because I can basically now make an analog averaging, but I'm cutting out the noise floor. And therefore, especially when one has so few photons, your convergence, your signal-to-noise ratio, which you get after a couple of images, is getting better because you sort of combine the noiseless behavior of a photon counter with the analog behavior of an integrator. Here it is. Okay, so that is now the analog integrated image, which takes 2 seconds data, 240 frames. We can even ask the photon rate. Should we then turn it? Okay, but that might be a bit, let me make it a bit faster, otherwise we don't see that. Let's say 8. Which color is the nicest? The Gus obviously prefers red. Maybe we go for a higher contrast. Let's take white. Okay, so let's see. So now when we turn this, you can see it turns. So, I mean, it's live, it's real time. And you see the advantage of having basically a video speed X-ray imager. Because when you're moving your stages or whatever, you get immediate feedback of what you're doing. Okay. So, did we have anything else? Metrology correction is not so much included here, as it has basically only this gap. One can put in metrology files for the display, which then can shift all the modules, but only Cartesian, right? Nevertheless, for the optical feedback, that works very well. And one can also turn the complete display. Depending on how you have orientated your detector, you can tell that to the DAC system so that the display displays it in the right orientation. So that left is left and top is top. Okay. Let's see. Yeah, that is the, let me kick out this one and go again into the raw spectrum. Here. Yeah, this one I said when I made the peak at that I got 89. It should be 88, but that's close enough. Yeah. Because the source does not make a monochromatic line. It makes a large amount of lines with the dominant parts here being 2, and therefore the peak gets a bit skewed. But the energy resolution of this imaging detector is not good enough to resolve anything like that. Okay. So then we take out the source again and put it in MIP finding mode and make the rest of the slides. Good. You want questions? Make it a discussion, or? Okay. So, some questions on the part of the demonstration. So I think we convinced everyone that it's really real, that it was not out of a conserve. And? Yeah. Yeah. Philip, do you have the Monte Carlo with the chart sharing? Okay. So we made a Monte Carlo and it more or less fits. Then, I mean, that's no news. That's also other detectors show that. PNCCD, we investigated that stuff in an endless effort because if you want to measure the spectroscopic lines, the iron emission of suns and the redshift, you really have to pin down the energy, and every shoulder, you know, could be Doppler shift. So you really want to get pinned down to your shoulder. CSPAD is not really good in recombining the energies because your noise, when you recombine 4 pixels, you double the noise, and so you get very quickly a big mess. The next generation detector, EPIX 100, will have a low enough noise of 50 electrons, so that there you can do charge reconstruction, and then you not only get a better energy estimate, but from the charge reconstruction you can also do sub-pixel resolution